Students, we're working on higher order derivatives today, and from that we will develop a function representing acceleration. So the first higher order derivative that we will consider is what's known as a second derivative, and a second derivative is the derivative of the first derivative. So the derivative of the first derivative. And the notation for this probably won't be too surprising. It will be f double prime, and that's actually how you say it. So you could have f double prime of x, you could have y double prime. If you use the dy dx notation, which you will need to be familiar with for a second derivative, it almost looks like an exponent. So it's the second derivative of y with respect to x, but you can see that both of those variables look like they have an exponent of 2. But that's just an indicator that we are wanting the second derivative. And then probably no surprise that a third derivative would be a derivative of the second derivative. And again, probably no surprise that the notation for that would be f triple prime of x or y triple prime. Now, honestly, we in this class at least do not go above the second derivative in terms of any applications. So I'm just letting you know that higher order derivatives are out there. And so even when we get ready to do the higher derivatives than third, we would just need to be aware that there is notation for that. Now, we don't continue to draw the primes. So once you've gone past a triple prime, then to note that we have a derivative, we just will put whatever number of derivative it is inside of parentheses with the function notation. So when you see that notation, you're looking for the nth derivative of that function. So like I said, our main work will be with first derivatives and second derivatives, but you need to know that other higher order derivatives do exist. So I thought we could go through the example that's shown on your papers there and practice doing the higher order derivatives. So I've given you f of x equals x plus 32 over x to the second. And I'd like for you to do f double prime of x, f triple prime of x, and the fourth derivative of x. So hopefully, as you're looking at this, you're thinking to yourself, well, I need to rewrite f of x, which you do. So we'll start with a rewrite. I'm going to put it up here. Not much of a rewrite, but a little bit. F of x equals, we can leave the x alone, but the 32 over x squared we'll need to write as 32x to the negative second power. You want to get that negative exponent so that you no longer have a variable in the denominator. And then since part A is asking you to do the second derivative, you hopefully will recognize that you need to know the first derivative. So I'll do that along with this. So after you do your rewrite, then do your first derivative. So the derivative of x is just 1, and the derivative of 32x to the negative 2 will bring the negative 2 multiplied by 32 to get negative 64x. And then remember to subtract 1 from the exponent. So x to the negative 3 power. All right, so now we're ready to work on what I asked for. So the second derivative, again, your notation's very important. So you're doing f double prime of x. And now we can do the derivative of 1. So we're looking here at the derivative of this first derivative. Well, the derivative of 1 is 0. And the derivative then of negative 64 x to the negative 3, we would multiply your negative 3 by negative 64 and get 192 x to the negative 4th. And depending on what you're using that for, you can either leave it like that, or you could put the x to the 4th in the denominator. But I think we'll just leave it as this. We'll look at f triple prime, so the third derivative, and so that's the derivative of the second derivative. And hopefully you'll start to see a pattern develop. So now you're going to take negative 4, your exponent, times 192. That's negative 768. And then x drops a power, so negative 5. And then your fourth derivative, so that's the notation we see here, would be the derivative of the third derivative. So we would take negative 5 times negative 768, and that would be 3,840, and then x, and we would drop an exponent to negative 6. So as you see this process unfolding, maybe you can make a conclusion about negative exponents, that when you're doing these higher order derivatives for negative exponents, they could go on forever. However, when you're working with positive exponents, eventually, when you're doing the derivative of another derivative of another derivative, eventually you will get to 0 and run out of derivatives. So that's just something that happens because of the exponents involved in doing a derivative. So that's your introduction to what a higher order derivative is. And then the rest of what we're going to do is look at how this is going to be used for applications that involve movement. So we're going to take a look at acceleration next. And this is at the bottom of your notes page. So on acceleration, we're going to define that in terms of the other functions that we've already looked at. So we have looked at the position function, and I've told you that many times we use S of t to represent position. So that would be generally your original function. So the most basic information is the position of an object. And then some more information about an object would be its velocity. And so hopefully you remember that the velocity, v of t, is found by doing the derivative of the position function. So velocity is the derivative of position. So maybe you can guess acceleration. Acceleration will be known as a of t. So a of t. And velocity, or excuse me, acceleration will be the derivative of velocity. But because of that, it's also the second derivative of the position. So you could do the second derivative of position and get to acceleration. And you might do that if you didn't need to know any information about the velocity. So keeping that in mind, we're going to look at an example with a chart. I want to talk about your units of measure and then do some comparisons using the chart. So we'll turn your papers over and look at the example that's on the back. So we have in this example a car traveling at a rate of 66 feet per second, which is 45 miles an hour. And then we have the brakes being applied, and the position function is given to you as S of t equals negative 8.25 t to the second plus 66t. It tells you that we have S measured in feet and t measured in seconds. So I'm asking you to complete this table, and I'm just going to go over the different functions. So S of t was given. Again, that was negative 8.25 t to the second power plus 66t. And then you're going to have a row for velocity. So velocity, v of t, which is the derivative of the position function. So we would do s prime of t, and that's going to equal, so we would take the 2 times the negative 8.25, that's going to be negative 16.5 t, and then your derivative of 66t is just going to be plus 66. And then acceleration. So a of t will equal v prime of t, which is also s double prime of t. So if we do the derivative of this negative 16.5 t, we would get just negative 16.5. The derivative of the 66 would be a 0. And so you can see the progression of the different derivatives. And then I also want to talk to you about the units of measure. So S of t is measured in feet. So our measurement for S of t would be feet. That's the position of this car. The velocity, since our time is measured in seconds, the velocity would be in feet per second. And then acceleration, and you'll have to remember that derivatives come from the limit definition where you are doing a division. And that division is by your change in x's, or in this time, it's your change in times. So if you already have feet per second and you're dividing that by seconds, then your unit of measure is going to be feet per second squared. And I would guess that would sound familiar to those of you that have gone through physics. All right, so now you're going to complete the table. And in the interest of time, I'll just go ahead and fill in the numbers. I would hope that if you needed to, you could use your calculator and fill those in. So you could go ahead and copy these things down. I'm just plugging in the different time values in place of t to get these values. So your positions at time 0, the car is at position 0, and by the time we get to 4 seconds, the car has traveled 132 feet and is now in position 132 feet. I want to make sure you can see that that is a plus 66. That didn't get written very well. All right. The velocity then, plugging in again those seconds into the velocity function. So negative 16.5 times t plus 66. And again, you could use a calculator as needed for these values. So we're plugging in the different times. Notice that this is instantaneous velocity. So in other words, we know the velocity at time 0 was 66 feet per second. We know it at 1 second. We know it at 2 seconds. We know it at 3 seconds. And finally, at 4 seconds, we know that the car has 0 velocity. So it has stopped. And then finally, we have the acceleration. Now, your acceleration is just a constant. It's negative 16.5, which actually isn't acceleration at all. Remember that velocity and acceleration are directional. So this is slowing down at a constant rate of negative 16.5 feet per second squared. So each one of these at the various times is negative 16.5 feet per second squared for in this case, it's actually deceleration. So keeping in mind that I just talked to you about instantaneous velocity, I'd like for us to look at average velocity. And for average velocity, I'm going to note that as V average. And then since I've got 2 intervals that I want you to look at, I'm going to put the interval identification on it. So we're looking at the interval from 2 to 3. Remember that average velocity takes 2 points, 2 ordered pairs. So you would need the position at time 2 and the position at time 3 in order to make your pairs. Or you could just use your formula, which is it's just the slope formula. So S of 3 minus S of 2 over 3 minus 2. And S of 3 from your table is 123.75. And then minus S of 2, which is 99. Your denominator is 1. And remember that this is measured in feet. This is measured in seconds. And so 123.75 minus 99 is going to give us a velocity average of 24.75 feet per second. And then we'll look at the second average velocity from time 3 to time 4. So average velocity from 3 to 4. And as soon as I can get this to right, we would do the same work. So S of 4 minus S of 3 over 4 minus 3. And looking at your table, S of 4 is 132 minus S of 3, 123.75. 123.75, and then over 1. And so that would give us an average velocity of 8.25 feet per second. And so as you look at the average velocities and you consider question C, now I'm not going to write out question C for you. I'll talk about it. I'll have it on the answer key that's posted online for your notes. But I don't think I'm going to try to write that out with this pen. But it asks how instantaneous velocity better describes what finally happens with the car in the situation. And so the table shows you instantaneous velocities. And with those, you know specific velocities at moments in time. So at time 3, you know how fast that car is going, or actually how slow it's going. And by time 4, you know that the car has stopped. And that's a better description rather than knowing that from time 2 to time 3, as we have in part B, that the car is going an average of 24.75 feet per second. That's the average. That's not actually what its speed was at any moment in time, possibly, but it is the average speed throughout that time from 2 to 3 seconds. Likewise, we see that the car slowed down between time 3 and time 4, but we don't have an accurate time when the car stops, when we're only looking at the average velocity. So as you answer part C, think about the fact that instantaneous velocity gives you information about a specific point in time, where average velocity is information about an interval of time. And so that's the example that I wanted us to consider using this new idea of acceleration. And then finally, I just have kind of a hodgepodge of examples on this set of notes. And I did want you to see this new idea of differential equations, just a brief introduction to that. Differential equations are, as it states there, equations that contain derivatives. And in this introduction, all I'm asking you to do is to verify that this given equation, y equals 2 sine of x plus 3, is a solution to the differential equation that has a derivative in it, y double prime plus y equals 3. So the work is very simple. You'll take the derivative, and in this case, you need to get to the second derivative, and you're going to make a substitution. So y prime, let me write that. I'm working with the original function. So y prime is equal to, all right, now we're doing the derivative of 2 sine of x. Well, that would be 2, and then the derivative of sine of x is cosine of x, and the derivative of 3 is just 0. So that's y prime. And then you need to do the second derivative because your differential equation has a second derivative in it. So the second derivative would be the derivative of the first one. So the derivative of 2 cosine of x, well, it would be 2 times the derivative of cosine, which is negative. So we'll have negative 2 times the sine of x. All right, now that you've gathered your information, you're ready to do, it's just an algebraic proof. You're going to substitute in to replace the y double prime and the y, and you want to verify that you get a true statement. So for y, so we're starting off with our differential equation, y double prime plus y equals 3. I'm going to substitute for y double prime the negative 2 sine of x and then I'll substitute in the y, so the original problem, which was, I'll put it in green, 2 sine of x plus 3. And then I have my equal sign, so equals 3. And hopefully you're seeing right away that you have some things that cancel. Negative 2 sine of x cancels with positive 2 sine of x, and you end up with the true statement that 3 equals 3, and therefore you have verified that y equals 2 times the sine of x plus 3 is a solution. And that's all that we're doing for this introduction to differential equations. We'll be working with those as we go on throughout the semester. So this concludes your lesson on higher order derivatives. And this will be the end of the unit that we'll do before taking a quiz. So good luck with your homework. Be sure that you continue to ask questions.